So let's look at these two parabolas, which I have not drawn wonderfully. I also have one decimal, so I should one decimals. So on the left side, we have the parabola y equals x squared minus 4. The vertex here, so if I want to find the x coordinate of the vertex, negative b over 2a, well, my b value is 0, right? There is no x term. So there is a b value that is 0. You could write this if you wanted to. If you really want to, you could write this as x squared plus 0x minus 4 to really emphasize the fact that your b value is 0. But if b is 0, then your vertex has an x coordinate of 0, and your y coordinate is going to be, if you plug in 0, 0 squared minus 4 is negative 4. Essentially, if you don't have a b term, your vertex is just your y-intercept, right? My y-intercept is also 0, negative 4. In fact, you could also think of this as just taking the graph of x squared and shifting it down 4. And if you take a graph that's y equals x squared where the vertex is at the origin and just move it down by 4, then the vertex is just going to move down to there. Not really the point, though. The x-intercepts are actually what I really want to focus on here. So to find the x-intercepts, we set x squared minus 4 equal to 0, and we factor. And x squared minus, well, you could also do it the other way, but I really want you to factor. It's especially important we factor here because we're going to see how the factors tell us how the intercept works. So I factored x squared minus 4. I got x minus 2 times x plus 2 equal to 0. And x minus 2 gives me the x-intercept positive 2. And the x plus 2 factor gives me the x-intercept x equal to negative 2. What I really, really, really want to point out here is that for these intercepts, when we graph it, the graph crosses the x-axis at those intercepts, right? Here and here. Right, at this x-intercept, the graph crosses, it starts out being positive and then crosses to being negative. And then at this other intercept here, it goes from being negative and crosses to being positive. The thing I want to show you about this one is actually kind of a different thing. So this parabola, y equals x squared minus 4x plus 4, it's got a vertex of negative b over 2a, which is negative negative 4 over 2, which is 2. The y coordinate is 2 squared minus 4 times 2 plus 4, which is 0. The y-intercept, if I plug in 0 for x, I get 0, 4. But again, the x-intercepts are what's really important here. So if I set this equal to 0, x squared minus 4x plus 4 factors as x minus 2 times x minus 2, which both give me a positive 2. But I should really just write this as x minus 2 squared equal to 0. So I see 2 as an x-intercept. And the thing I want to point out that is different from this one to these ones over here is that at this intercept, right, we come down, since there's only one intercept, we hit this y-intercept, and then at the x-intercept here, we bounce off the x-axis. And the reason for that, or one reason for that, or I should say a connection we can make, is that when your x-intercept, which is 2, comes from a factor that is raised to an even power, our graph is going to end up bouncing off the x-axis. On the other hand, when our x-intercepts come from factors that have odd powers, right, both of those factors are raised to the first power, which is an odd number, then when your intercept comes from a factor with an odd power, we end up having the graph crossing the x-axis. We could also make a sine chart to make this even more obvious. So I make a sine chart for my function y equal to, I'm going to write it factored, x minus 2 times x plus 2. We know it's 0 at negative 2 and 2. And then I can just pick numbers in each section. If I pick 3, 3 minus 2 is 1, 3 plus 2 is 5, 1 times 5 is positive. If I pick 0 in between negative 2 and 2, I know I'm going to get negative 4 because if I plug in 0, I get negative 4. But I can also do it here. Negative 2 times positive 2 is negative 4. And if I pick something like negative 3 out here, negative 3 minus 2 is negative. Negative 3 plus 2 is also negative. And then negative times negative is positive. And this sine chart exactly matches up with whether or not the graph is positive, right? Here we're positive above the x-axis. Here we're negative below the x-axis. And we go from being positive until we get to -2, and then negative from -2 to 2, and then positive once again. So when you change signs from being positive to negative, you cross the x-axis. When you don't change signs, that's when you bounce off. So for this one, the sine chart, the only place where this is equal to 0 is at +2. And we can see that, oh yeah, x minus 2 squared, whatever I plug in that isn't 2 is going to make it positive. So if I plug in 3, 3 minus 2 is 1, and 1 squared is positive. If I plug in -2, or 0, I plug in 0, 0 minus 2 is -2, and -2 squared is also positive. It's +4. So here, since the sign doesn't change, when we go from this side of our intercept to this side of our intercept, we are bouncing off. We're staying on the same side of the x-axis. So when we graph higher order polynomials, which we're about to do, we're going to use this fact that when you have a factor of your polynomial raised to an odd power, the x-intercept that corresponds to that is going to cross, the graph is going to cross the x-axis at that x-intercept. Whereas if you have a factor that has an even power, the graph is going to bounce off the x-axis at the corresponding x-intercept. And that's kind of the only thing we really, there's like one other thing we kind of need, but mostly that's it. That's how we're going to graph most of the polynomials we're going to see. And yeah, let's look at some examples. So I hope everyone's doing all right. So yeah, I wrote a whole bunch of, I wrote words. Those are all just words, examples. Let's look at a higher order example. Let's look at y equal to x cubed minus 3x squared. Also, I posted a couple of videos of me graphing some parabolas. They are on Canvas in the modules. You can find them if you want more examples. Yeah. So I want to graph this thing. And to graph something that's not a parabola, we're going to follow kind of a different method, right? So for parabolas, you always find the vertex, and then the y-intercept, and then the x-intercept if we have any. Other higher degree polynomials don't really have a vertex, so we don't look for a vertex unless it's a parabola. So just want to point that out. No vertex unless we know it's a parabola, unless it is second degree or quadratic. Quadratic functions are the only ones that really have vertexes. Actually, that's not true. I should say absolute value functions also have something called a vertex, but most functions don't have a vertex. So we're going to graph this one, and we're going to do what I think is a normal kind of thing. We're going to, 1, find the y-intercept, and 2, find any x-intercept, and then kind of talk about them. So first things first, let's find the y-intercept. To find the y-intercept, we're just going to set x equal to 0. We set x equal to 0, we're going to get y equal to 0 cubed minus 3 times 0 squared. That's 0 minus 0, which is 0. No big surprise. To find the x-intercepts, you're going to set this equal to 0, and you're going to want to factor. In fact, we probably wanted to factor it from the get-go. It's usually a good idea for these higher order polynomials or higher degree polynomials that we do go ahead and just factor it. So I see I can factor out a greatest common factor of x squared, and I'm left with x squared times x minus 3. That just helps me. So then I'm really solving x squared times x minus 3 equal to 0. And we can see the solutions. From x squared equal to 0, we're going to get x equal to 0. And from x minus 3 equal to 0, we're going to get x equal to 3. And now I'm going to start plotting things. Plotting your demise. No, not really. Okay, so my y-intercept is the origin, which is 0, 0. And my x-intercepts are also the origin, and also x equals 3. Okay, and how did I want to say this one? So I'm going to make a sine chart here, and then we're going to kind of make some connections back to the powers of our factors. So different color. One sec. Here's my sine chart. And on my sine chart, the only numbers that you really ever want to put on your sine chart are the values of the x-intercepts. I only want 0, I only want 3 in this particular example. Because those are the only places where the sign of the function can actually change. To change from positive to negative or negative to positive, you have to go through 0. So pick a number larger than 3 and plug it into your function. Now here's the thing. I don't want to plug it into this unfactored thing. If I picked 4, I don't want to do 4 cubed minus 3 times 4 squared. That's more work than we need to do. Instead, we should always use the factored form, because I don't actually care what the value is, I just care what the sign is. I plug in 4 here, I get 4 squared times 4 minus 3. 4 squared is positive, 4 minus 3 is positive, and positive times a positive is positive. So I know that over here, when I pick a number bigger than 3, it's got to be positive. And then I could keep picking numbers. I could pick 1. I plug in 1. 1 squared is positive. 1 minus 3 is negative. A positive times a negative is negative. I could pick negative 1. Negative 1 squared is also positive. Negative 1 minus 3 is negative. So a positive times a negative is still negative. But instead of picking values like that, we also could have done the following. We could have said, well, look, 3 came from this factor. And this factor, x minus 3, has an odd power. And when the power is odd, we cross. And crossing is the same as changing signs from positive to negative or negative to positive. And then at 0, well, 0 came from x squared. Our factor is raised to an even power, so the sign stays the same. We bounce off. Okay, we're bouncing off. So here's, right, we go from negative to negative, we're staying the same. So over here, and really, I mean, the sine chart's going to help me graph it. So over here, left of 0, my function is negative. So I'm going to be negative. I'm going to hit there, and I'm going to bounce off, right? Because I'm going from negative, I'm staying negative over here. And then I have to turn around so I can hit this next intercept and cross through, because I have to cross into the positive territory. And that's how we would draw a graph like this. One thing you might wonder about is this point right here, which is called a local minimum, right? It's smaller than all the things that are next to it. Without calculus, we don't have the tools to figure out what that point is, so don't worry about it. Eventually, when you take 16A or 17A or 21A, you will learn about, or you might learn about, but you will learn again about how to find a relative minimum point or relative maximum. We can see that this one is a relative maximum at 0, 0 because it bounces there, but generally we can find all of them using calculus. Words. So some of the words here is, that I have not used yet is for x equal to 0, we would say the multiplicity of that x-intercept is just the power of the factor associated with it. So for x equals 0, the multiplicity is 2. For x equals 3, the multiplicity is 1. So the multiplicity is just the power of the factor the intercept came from. And if the multiplicity is even, we know we're going to bounce. If the multiplicity is odd, we know we're going to cross. That's kind of most of the whole story here. Yeah, I might say something else, but really that's kind of it. So as is usual, I'm always trying to graph things as efficiently as possible, meaning I don't really want to do more work than I have to do. I mean, it's okay, but we're trying to not repeat work. So let's take a look here. Come on, sorry. Thumbs, I'm all thumbs, okay. So let's graph another one. Here's one that's, ooh, I don't want my water to fall. That would be terrible. Okay, so let's try graphing one that isn't already factored for us. So we're going to graph, and I'm going to use function notation, right? F of x equal to negative x to the fourth plus 5x cubed minus 6x squared. So what's the greatest common factor I could pull out?
X squared.
Totally. And although, yes, I would say x squared as well, I'm actually going to factor out a negative x squared, so that the thing that's left behind has a positive coefficient and is kind of easier to deal with. But if I just factored out x squared, I'd be left with negative x squared plus 5x minus 6. And although I know I can factor that, to me, the negative here is just challenging. So I would rather make my life easier and factor out the negative x squared and be left with a positive x squared minus 5x plus 6. Right? We're totally allowed to do that. It's perfectly fine. And then I'm going to factor, so we're going to factor as much as possible. So this factors even further as negative x squared. We're trying to multiply the 6 and add up to negative 5, so we want a minus 2 and a minus 3. So that's how that factors. I'm getting a little raspy here. It's terrible. All right. So we're going to find the y-intercept. For a lot of these, you're going to get some power of x factoring out, which means you're going to get a y-intercept of 0. Not always, but a lot of the time. So here our y-intercept is 0, right? If I plug in 0, f of 0, if I set x equal to 0, I'm going to get 0 times, it doesn't matter, right? I don't think you need to write any of this out. I think you should just say it's 0. You could write it's negative 0 squared times 0 times anything, 0. You could write this. It feels silly. Don't write that. Just write 0. If you're multiplying by 0, you just 0. The x-intercepts are where it's at, really. So for the x-intercepts, we're setting this equal to 0. So negative x squared times x minus 2 times x minus 3 equals 0. And I'm just going to say x equals 3, x equals 2. And here you could write x squared equal to 0, but we know really just the inside part has to be 0. So I'm just going to get x equal to 0 here. All right, so let me ask you guys a question. You can either show me on your fingers, you can type it in the chat, you can say words. For x equal to 3, what's the multiplicity? What's the power that comes with the factor?
First.
Exactly. The multiplicity of 1. This is not meant to be a hard question. For x equal to 2, what's the multiplicity? Oh, yeah, okay, sorry. I have to look at the chat if I say you guys can write things in the chat. Good call. And then for x equal to 0, what's the multiplicity? Yeah, exactly. Exactly 2. So that's going to help me graph this thing. So I'm going to plot my points, 0, 2, and 3. Sorry, my x-intercepts, 0, 2, and 3. As well as my y-intercept, which is also the origin. And then I'm going to, so I know, so here's kind of an issue that we're going to run into when we have specifically the origin as one of our intercepts. We need more information. I don't know if I'm, in fact, let me actually, yeah. I don't know. Here's what I do know. I do know I bounce at 0. And I do know I go through at, oh, I forgot one of my points. I do know that I go through at 2 and at 3. But here's the problem. I don't know if my graph looks like this. Bounce at 0, go through at 2 and through at 3. right? I don't know if it looks like that, or if it looks like that flipped over, right? Where it would be, I think I can draw it again. Right? It could look like that. Or it could look like that. So how do I know which one it is? Well, I can either do the whole finding of a sine chart. That's really more work than I want to do. Big surprise. All you actually need is one more point. So if you can find one point that's either above or below the x-axis, then you'll know which of these you have to beat. So pick any value of x that isn't one of your intercepts. I'm going to pick 1. If I pick 1 for x, y is going to be f of 1. And f of 1 is -1 squared. So be careful. This is a -1 squared where the squaring happens before the negative. So it's going to be a -1 times -1 times -2. And the negative times a negative times a negative is a negative. So I know that at 1, when x is 1, the y value is -2. So it couldn't be this graph here, because that's a positive y value. So it's got to be this graph here, where at +1, we're getting -2. So if I was graphing this, what I really would have done if I was graphing this like I'm not actually graphing it, I would have found those 3 x-intercepts, and then I said, okay, I also have the point 1, -2. So there's my point 1, -2. And then I know from here, if I go towards that x-intercept, at 0 I have to bounce. If I go the other way, from here at this x-intercept I have to go through, and then I have to go through again. So the bouncing or the crossing kind of tells us the whole story about what the graph is going to look like. Now, is this graph perfect? Not at all, right? If you actually graph this thing on, oh, ouch, I just hit my heel with my wheel. That's one reason to wear shoes, is so your feet are protected from your chair. Anyway, so if we look at Desmos here, just to kind of see things, just want to show you that this graph is by no means perfect. It doesn't have to be though. So let's graph this. Y equals, and I need to share my graph. Let's see. Share the thing. Sorry, 1 sec. There we go. So we actually look on Desmos just to compare what I've drawn versus what it actually looks like. I've got, let's see, it's easiest to put it in as, well, let's do it factors. -x squared times x minus 2 times x minus 3. Oops. So I made a little mistake when I graphed that. I accidentally got those other factors up as in the power. So I need to like press return, I think. Nope, that doesn't help. Let's do a space maybe. Nope, I mean, I see delete it. Let's try that again. Sorry. Sometimes you make little mistakes. X minus 2 times x minus 3. So there's what it looks like. So definitely, right, it's got the same shape as what I've drawn, right? We are starting over here negative. We go up, we bounce off 0, stay negative. There's some minimum there. So that value, I'm not particularly familiar with it, but Desmos will show you where relative maxima and minima occur. And then we continue on to 2, and then we cross through, and then we turn around so that we can hit 3 and cross through. Just like my graph did, but obviously they don't look exactly the same. That's okay. Your graphs are not going to look perfect. They shouldn't look perfect. Yeah. You can always look at Desmos to kind of see if your graph looks kind of right. Although, really, as with most things, I would like you to try to do the graphing without using other stuff until you've actually done it. But you're welcome to check your own work. Come on, board. Sorry, 1 sec. My wife is sending me a message, and I think I actually respond to it. One moment, please. Let's see. So back to where we were. Oh, that's not. That's not. Sorry, my brain just went away. So anything else I want to say about that example? No, I think we're good. Yeah. All right. So let's look at a few more. I feel like there was another thing to say here. Oh, I know what it is. Now we'll do that. We'll do that in a minute. Sure. There is another thing about polynomial graphs that you can tell by looking at the graph, which I haven't mentioned yet, which I think I wasn't really planning on talking about it, but it does seem worthwhile, and we've got time. So I'll probably say something after this example about it. Let's go ahead and look at another example. So we're going to graph the following: y equal to x cubed plus x squared minus 9x minus 9. So if I give you a graph that is a degree higher than 2, and it's not already factored for you, you can expect that it's going to factor in some relatively obvious way. This one's going to factor by grouping. So I can factor this as plug x squared here, multiple x plus 1. I can factor the negative 9 here, and I'm up to the x plus 1. So then from each of these, I can factor out the x plus 1. And I'm left with an x squared here and a minus 9 there. And then I can factor that even more, because x squared minus 9 also factors. It factors as x minus 3 times x plus 3. So there we have fully factored it. Let's find the things. So let's find the y-intercept. Now, something to say about the y-intercept here. If I'm finding the y-intercept, I'm plugging in 0 for x. Is it going to be easier to find the y-intercept if I use this first version of the equation where I haven't factored things, or this last version where I have factored? Which one is it easier to plug in 0 for? This one or this one? It doesn't really matter. Someone was going to say something. You can say something if you want.
Oh, I was going to say the factored one.
So the factor one is a perfectly fine choice. I do think we have to do a little bit more work if we pick the factor one, but it still will work. If I plug in 0 here, 0 plus 1 is 1, 0 minus 3 is minus 3, 0 plus 3 is 3, 1 times negative 3 times 3 is negative 9. I personally do think it is slightly easier to find the y-intercept by plugging in 0 here. So you plug in 0 here, you just get 0 plus 0 minus 0 minus 9. But either choice is correct. So do whichever one you like. So we're going to get x equal to 0, we're going to get y equal to negative 9. So our y-intercept is 0, negative 9. Our x-intercepts should be pretty straightforward to see. In fact, I'm not even going to write this again. I'm just going to say, I know I'm setting this whole thing equal to 0. So I should be getting, from this factor, I should be getting x equal to negative 1. From this factor, I should be getting x equal to 3. And from this factor, I should be getting x equal to negative 3. And again, that's because we're setting each factor equal to 0. So what's the multiplicity? What's the multiplicity of all of them, actually?
1.
Yeah. Each of them have a multiplicity of 1. You don't need to write these powers up here, but you can. Which means each of them is going to cross the x-axis. Now here's the really nice thing about this graph versus the previous one. When you have a y-intercept that isn't the origin, you kind of have all of the information you need to graph it. So my y-intercept is negative 9. My x-intercepts are -1, -3, and +3. My graph is definitely not to scale. That's okay. Okay, so I know I have to go through this point, and then I'm going to cross each of these. So from here, if I went to the left, I'd have to hit this x-intercept first and cross through, and then I'd have to turn around and cross through that one. If I go to the right, I have to just cross through that one there. So having a y-intercept that isn't the origin kind of gives you information. So I know I'm going to be, let's see, I said I was going to cross and then cross. So if I start down here, I cross, I hit my y-intercept, and then I cross again. We never use the language of crossing or bouncing off your y-intercept because it's not the same sort of thing. For the y-intercept, you're just moving through from left to right. So I guess you're always technically crossing your y-intercept, but we don't, that's not the same idea. I will point out, if we had mistakenly started in the wrong place, it wouldn't have worked. So if we start up here, like let's say, so this is wrong, you don't want to write stuff. If we started up here, we would have to cross here, and then cross here, but then there's really no way to get down to this y-intercept without maybe crossing again, but then you're adding in an extra x-intercept that we didn't have. So that's clearly not the right way to go. There's only one way that's going to work. Where is that? So another way to kind of talk about this is through the language of end behavior. So I don't know if you're familiar with this or not, but graphs, polynomial graphs, we always know do one of four things at the end. So when I draw a polynomial, if I'm going out to the right, it's either going to go up to infinity like this, or is the other one go down? No, the other one goes up to, oh well. These ones actually have the same kind of shape, right? So both of these have the same end behavior. Both of them are up to infinity on the right and down to infinity on the left. And that's because they both have the same sort of things that classify your end behavior. Both of these have an odd highest power and a positive leading coefficient. Odd highest power, positive leading coefficient. So, yeah, let me do this. So I don't think you need to use end behavior to do this work, but it is something people like to consider. And so I just want to tell you kind of the usual deal. So end behavior. People often make a little chart. So there's two, what's the word I'm looking for? There are two properties of your polynomial that determine the end behavior. And that's the degree, which is just the highest power, and whether it's even or odd. And then there's the leading coefficient, whether it's positive or negative. So if your degree is even and your leading coefficient is positive, the left side is going up and the right side is going up. The example I think of is y equal to positive x squared. That looks like this, where the left side's up and the right side's up. And then if the degree is even and the leading coefficient is negative, the left side and the right side are both going down. And my favorite example of that is y equal to negative x squared, which is just this one flipped over. Looks like that. So what I always think about is if the degree, if the highest power is even, both sides do the same thing. They're either both up or both down. And then if the degree is odd, the sides do opposite things. One side's up, one side's One side's up, one side's down, or one side's up, one side's down. So when it's a odd and positive leading coefficient, the right side's up, the left side's down. My usual graph I think of is something like y equals positive x cubed, which looks like that. Or this example here. Here is a polynomial whose leading coefficient is positive and whose degree is odd. And it definitely is down on the left, up on the right. And finally, the only other combination of up and down that we haven't gotten to is up on the left and down on the right. And that's when your leading coefficient is negative and your degree is odd. And that example, the base case example I was thinking of is y equals to negative x cubed. That looks like that. So that's kind of, you can use M behavior to kind of help you figure out where you start. So let's see, do I have, yeah, we'll do that for the next one. Not the next one, not that one. Let's do this one. So, no, sorry. How much time? Oh, okay, I got 11 minutes. I need to stop fooling around. So none of the homework problems I've asked you to use the M behavior, but you're certainly welcome to use that if it's helpful to you. Let's look at the following. On a graph, f of x equal to negative x minus 1 cubed times x plus 2 squared. Yeah. All right, so we're going to do it the way we've been doing it. We're going to find the y-intercept and the x-intercept, and then we'll talk about it. So y-intercept, I'm going to set x equal to 0. F of 0 is going to be negative 0 minus 1 cubed times 0 plus 2 squared. Negative 1 cubed is negative 1, so I get negative 1, and then 2 squared is 4. So negative 1 times 4 is going to be positive 4. My y-intercept is 0, 4. My x-intercepts, so if I'm setting this whole thing equal to 0, here I'm going to get x equal to 1. Here I'm going to get x equal to negative 2. X equal to 1. I don't even really care what the number is. I just care if it's odd or even. But the multiplicity of x equal to 1 is odd. It's 3, which means we're going to cross. And the multiplicity of x equal to negative 2 is even. It's 2. So it means we're going to bounce. Okay. Now we could also discuss the M behavior if we wanted to. The issue with the M behavior is you have to think about what it would look like in the standard form, meaning you have to be able to at least kind of envision what this looks like, or at least the first term looks like if you multiply it all out. Which I don't really want to do. I don't actually want to multiply it all out. But I know that if I did, here's what would happen. X minus 1 cubed would give me x cubed plus some lower terms. I don't really care about the lower power terms. X plus 2 squared would be x squared. It would be x squared plus 4x plus 4. But again, I don't care about the lower power terms. And then if I multiply these together, x cubed times x squared would give me x to the 5th. So I get a negative x to the 5th and then smaller things. So here I can see that my leading coefficient is negative. My degree is 5, which is odd, which means I'm in this situation where the leading coefficient is negative and the highest power is odd. So it's going to be up on the left and down on the right. So my end behavior is up on the left, down on the right. We don't really need that in this case, but it's still helpful to have. Now we're going to graph it. So let's see, I've got my y-intercept of 4. I've got my x-intercept of +1 and -2. And we'll label them after, but there we go. So I know at -2, I have to bounce. So here's the thing. Since I have to bounce here, so everyone should be watching, I can't bounce like this. Because if I bounce like this, then I won't be able to get up there. So I have to bounce like this. That's the only way I'm guaranteed to hit the y-intercept. So because we have a y-intercept that's not the origin, it kind of tells us which side of the x-axis things have to live on. I don't like the way I've drawn that, so I'm going to try and fix it. It's going to be more like... Sometimes things are a little too close together, right? And then here we're going to go through. Yeah, we're going to go through. This is not probably at all what the graph really looks like. It probably looks very different than this. But that's not important. One thing I do want to point out is if the y-intercept is like, right, like it's the top of kind of a hump here, it doesn't have to actually be the top. I know a lot of people would probably usually choose to draw this so that that point actually was the very top. It's fine to draw it that way. Just know that it probably actually isn't. So I know a lot of people would want to draw it like that. Perfectly fine to draw it like that. But if we actually look at Desmos, I'm sure we will see that that's not the top point. So let's take a look real quick like here. Yeah, I still have time. I got time for one more. Oops. Oh, that's fine. So let's see if I throw that graph in the thing. Negative x minus 1 cubed times, what have I got here? X plus 2 squared. So it does have the same look, right? It's going down from left to right and it's bouncing at -2. And then it's coming back and hitting 4. And then it's coming down and hitting +1. But clearly, right, the graph has more nuance than what we are able to kind of see with just the work we're doing, which is okay. There's something else I want to say. Oh, I do want to point out, right, our end behavior certainly corresponds to what we've drawn, right? Our graph is actually up on the left and down on the right. All right, let's try one more. We won't get to my very last example. That's all right. Maybe I'll do a video of the last one. I'll try not to fall into it. If you guys look at the parabola videos, you'll see a very short video in the second one below the first video of me kind of almost dying. Not really, just almost falling. I thought it was kind of funny, so if you want to see that, you can go watch it. It's on Canvas. It's like 18 seconds. All right, let's try this. X cubed times x plus 5 squared times x minus 4 to the 5th. Okay, so y-intercept, easy, it's going to be 0, because you plug in 0 for y. This x cubed by itself means you have 0 times stuff. So x is 0, y is 0. Another way to think about it is if you see that x equal to 0 is going to be an x-intercept, that means that the y-intercept is also 0. X-intercepts. So let's see, let's use some green pen here. So from this factor, we're going to get x equal to 0 with a multiplicity of what?
3.
Yeah. Okay, what's this? What x-intercept are we going to get from this one? X equal to -5 with a multiplicity of 2. And from this last one, we're going to get x equal to 4 with a multiplicity of 5. And then we're going to start graphing it. Oh, and so you don't have to write, right? So we know it's going to cross, it's going to bounce, it's going to cross. And it probably would be a good idea if I thought to do it, to write these in order of in least to most. So it might be more helpful to actually write it as like -5 first and 0 second. Just because then we're graphing it, it's easier to see what's happening. So this one. Not that you need to redo this, but I'm just saying it's kind of nice. X equals -5 has multiples to 2, and then x equals 0 has multiples to 3. So when I graph them, -5 is over here, and then 0, and then 4. Now, here's where we're running back into that problem where our y-intercept is 0. So I don't really know if I'm above or below. Like in the previous one, my y-intercept being up here forced this bouncy part to have to go that way, and forced this crossing part to have to go that way instead of going like this way. But here, since our y-intercept is on the x-axis, we're not forced to one side or the other. So we can either do what we did before and find an extra point, or, and this is kind of where the end behavior actually usually comes into play, we could use the end behavior. So let me ask you guys, if we multiplied this out, what would be the highest power of x? Any guesses? It might be related to how many somethings you have on your hands.
If we multiply it out, would it be 5?
Wouldn't quite be 5, although you're on the right track. If I multiply these two parts out, I get 5. But then I also have this part here. So actually, the way you can find the degree, as long as each of the inner things is just x plus or minus something, is by adding these powers. Or similarly, adding the multiplicities together. 2 plus 3 plus 5 is 10. So the degree is 10. If you multiply this out, right, x plus 5, so this would equal x cubed. X plus 5 squared is x squared plus 10x plus 25. And x minus 4 to the 5th is x to the 5th times other stuff. And then if you look at the highest power terms, right, these have to get multiplied together at some point. And when you multiply things with the same base together, we add the powers. And 3 plus 2 plus 5 is 10. But the faster way, the easier way, is just to say, add the multiplicities together. That'll always give you the degree. Okay, we're almost done. So then let me ask you. Oh, brain, we're happy. Oh yeah, if you multiply this out, would your leading coefficient be positive or negative? Do I have any negatives in my first term?
Positive?
Yeah, it's definitely positive. You only ever really get a negative leading coefficient if you have a negative out in front, or if you have a negative x somewhere inside here, but it can be a little dicey. So our leading coefficient is positive, which means since our degree is even, we're both up or both down. But since our leading coefficient is positive, we are both up. So here's what I do with that information. I usually like to go from left to right, because that's usually kind of how we graph things. I'm going to go further left than my leftmost point that I know, my leftmost intercept. So I'm going to go left of this one. I'm going to go over here. And I know left of that point I have to go. And then I'm just going to come down, I'm going to hit that -5. I'm going to bounce off, because -5 is a bouncer. And then I have to hit that x-intercept of 0. That's going to go through, because the multiplicity is 3. And then I'm going to turn back around so I can hit 4, and I'm also going to go through there. And assuming I've done things right, if I bounce and cross accordingly, I should end up going the right direction for my end behavior to be correct at the end. And it is. All right, that's all I've got for today.